it pops up one of those mirrors that you have over there. Yeah, it pops up a convex.
Other user, admin. Apparently it's okay with that.
So this one has to restart that next week?
Why does technology hate me today? I'm gonna restart, because sometimes that's the way to get past it. All right, well, that's trying to come on. And Thomas, you said something else that my mind was elsewhere at that
There it
moment.
is.
Or
I
Aaron said?
found a video.
Oh, you found it? Okay.
They got, it's like a little pig figurine instead, though. It looks like it's floating on. It looks like it's floating on top.
Yep.
But he takes off that bulb off the top and shows that the pig's actually laying at the bottom. And it's actually backwards too. Facing the
Yeah.
other way.
Yeah, because I noticed that before, because usually it's a coin and I don't pay attention to
Yeah.
where the coin's facing.
Huh. That's interesting.
It's science. I saw a slogan the other day for science. Science, it reduces the stupid. All right.
I like to also say that undiscovered science is magic.
There's a,
Well, I could
the
find.
classic sci-fi mantra.
Wait, that is I didn't know that, but
Technology sufficiently advanced, it appears like magic.
yeah, that is also true.
Like electronics run on smoke.
What?
Electronics run on smoke. If you see smoke coming out, that means it doesn't work anymore.
True. And also be sure to watch out for whiskers.
20-foot-old dive. What's that smell?
We're done it.
We get done at 12:20.
How much farther in advance? You know what, I'm not gonna zoom on ahead at this point. So, at this point, let's talk a little bit, let's sort of drop back to chapter 33 before I zip on to chapter 35.
Wait, are we doing a lab today?
Yeah. So I have a light source here that's booming out, beaming out light in all directions. So we talked about the radiant flux is the amount of power, the energy per unit time that's being released from it. But not all of that is visible, so what we care about is the visible light. So then we get into luminous flux, and then if we narrow it down, we get into luminous intensity within a certain area here. And then the amount that actually hits a target, we get into illuminance. So, radiant. And I want to make sure I get the vocab right. All right, so radiant power is emitted. Luminous flux is visible. Then for solid angle, we have luminous intensity. And then illuminance is what actually hits a surface, and then it would be luminance which bounces off. But we care about the illuminance because we have sensors that are gonna detect what is actually hitting the surface. We have basically a sensor for that. The units for this is lux. And so I would expect, as this light goes out in every direction, we don't have a mirror on one side, it's not a spotlight, it's just gonna be a regular light bulb that goes out in every direction. So what would you expect for the illuminance to be as you move back?
It would decrease, wouldn't it, because the angle's getting smaller?
Um,
I think it's all.
Not because the angle is getting smaller. Actually, the angle, see, if I'm shining the light like this,
Further back.
if it's a spotlight, as I move farther back, that's not really changing the angle which it's coming out. As we move back,
No, I mean like the solid angle where the light
Oh.
is actually hitting the target.
that's right. If I have a finite sized target here, then as I move back, the angle would get smaller. Okay. I'll lie that.
That's what I was saying.
Okay, I apologize, yep. What about in terms of the relationship? It should get smaller. We should have lower luminance the farther out we get. Because think about the light as it's shining outwards. If I think about a pulse of light, so basically I get this sphere of, this shell of, thin-shelled sphere of light that is booming outwards. Illuminance does not depend upon the angle, that's the luminous intensity. The illuminance depends upon the area of what we're seeing here. So I'm going to have a sensor of some particular size here. As it hits that, I'm getting one small little fraction of the overall amount of light that gets pulsed out. If I double the distance from the light source, so if that's double the distance, what would I expect to happen to the illuminance?
I would imagine the luminance would get greater. Like say if I shine a light up the wall, if I'm up close to it, it's covers a small area. As I get farther away, that area expands.
All right, but the difference is, in this case, I have
It's just a small sensor.
I have a finite size sensor.
Yeah.
So the sensor is not changing. What would I expect the luminance to be in this case?
I feel like for the sensor it'd be smaller because now there's less I can't get the vocabulary right with this, but basically there's the light isn't as strong, yeah, intense as it was, so the closer it was. So it's
All right.
I don't know.
And
My wording's kind of bad here, but
the luminance should drop because it is farther away, because I'll agree with it's not as intense. Not as many photons are hitting the sensor.
Mhm.
But if I double the distance, how much should the illuminance drop? By what factor?
I don't feel like it's proportional.
If we took let's just, for the sake of argument, let's just say that this is my sensor right here. I've got a finite size. And so right now, if this is the shell or the sphere of light that's coming out, and may have to do this in front of a camera. If this represents the amount of light that's coming out, and I have the sensor, just think about that. This tip of my pen here covers a certain fraction of that light. As the light goes out and expands, that fraction gets smaller. So the amount of area that's hitting is the same, but as it expands, what is the relationship between the radius of the light pulse and the amount of light that would be hitting this.
Is luminous flux over distance square.
Because the surface area of the sphere is 4 pi r squared. So as the radius increases, basically we take that same amount of energy that we had to start with, except we're spreading it out over the entire surface. So since it's a r squared relationship, if I double the radius, I should be getting 1/4 of the illuminance. Mathematically, let's make sure. So we have our luminous intensity divided by r squared. And so that's one of the things that we are exploring here. Now, the solid angle is getting smaller as we pull out, and so that's something that you'll, in theory, address in one of the analysis questions. The other bit is, this is getting the full-on amount, but so now I have my finite sensor, and just for the visualization, I'll use a marker for my sensor at the moment. We do have more sophisticated sensors than a 10. So this one's getting sort of the maximum amount of light hitting it, but suppose I tilt it. What effect does that have?
Is the Russian time with cosine of theta.
Yep. So it does reduce the amount of light that's hitting it, because if I have light that's streaming in like this, if I have a sensor there, I'm going to get it all. But if I tilt my sensor, well, some of that light's just going to pass it right by. And so I'm going to get a smaller bit of the amount of light hitting it. And so there's a cosine theta aspect to it. Now you got to be careful when you're doing the cosine theta bit, because if I've got light, and we'll be using the tracks up there. So I have a light bulb right here or somewhere around there, and I have my sensor. So the first part of the lab is you'll have the sensor here, and you'll just be moving the sensor back to various distances. And then as you tilt it, you got to be careful, because you want to make sure that the sensor here is still basically, the center of the sensor basically stays in one spot as you rotate. So as you rotate this, try to do it from that point of view, you want this part to maintain its position. And so,
You want it the same distance from the light source, pretty much.
yes, yeah. Now, for doing these labs, a number of these labs,
Yeah, I felt that.
at least that wasn't videoed. We'll be using these tracks here. It has a meter stick or a metric measure, I guess it's a little more than 1.2 meters. And some of them, yeah, and it can slide. So you can establish zero someplace. Just recognize this slides easily. So if you keep it on the ends like that, then it's easy enough to set if it gets knocked. But if you want to, you can slide this so that you can make zero wherever you want it to be. The math might be just slightly simpler, but just keep that in mind. And we have various light sources here. There we go. And then we'll have these tracks right here, so that the light source actually will be slightly offset. This. So the light source will be centered here, not directly over the track, but just slightly off the track. So something to keep in mind. Why don't I actually hand out the lab, stop the recording.